problem. Oh, I see. Okay. That's the one. Why are you over there? Okay. Alrighty, let's connect this and start. Wait a second. Why is this so small? That's better. Wait a second, now my webcam's not working. Oh, how annoying. Alright, let's see if we can't figure this one out too. Okay, let's try this once more. Video input. Okay, well, for whatever reason, it is not showing my face today. Yeah, probably Brittany, that's exactly what's happening. Okay, well, whatever. I guess I will deal with my webcam later. Sad. But we can continue our exciting exploration of thermodynamics. Yay! So last time we talked about this idea of enthalpy with phase changes. And so we remember we kind of had, solids, liquids, and gases, right? Like that's kind of what we were discussing yesterday, or Wednesday, I guess, almost a week ago. Here, let me try unplugging it. Let's see. Feels so strange to not see myself there, but let's see if that fixes anything. Maybe not, but we'll see. Okay, anyways, so let's go ahead and remember we had some terminology for all of these changes. Let's see. Yeah, let's do one of them in like this, right? We had liquids turning into, or solids turning into liquids. We had melting, right? And do we remember, was that an exothermic or endothermic process when we're talking about melting? Let's say evaporation. Was melting going to be exo or endothermic? Yeah, right. And so remember that we have a positive sign that's associated with endothermic transitions. Evaporation was also endothermic. Just so we have it here, this was endothermic, right? Alrighty, and so it turns out we can also go directly from solid to gas, which is called sublimation. This is what dry ice does. That's probably the most common example that you probably would have seen in your everyday life. So carbon or dry ice is solid carbon dioxide, and it just goes ahead and turns into a gas. It doesn't actually turn into a liquid first, so it goes directly there. And yeah, that one is definitely going to be endothermic as well. So all of these three are going to be endothermic. So just so we know, the delta H for sublimation is going to be the delta H Remember, fusion meant melting or freezing. And it's also going to be, we add that to the delta H for vaporization. So essentially, we're just kind of skipping that stop at liquid. We're just going directly from solid to gas. And as a result, the energy change, the heat change rather, is going to be equal to the heat changes from solid to liquid and liquid to gas. So we're not going to really calculate stuff with that, but there it is, just so we all know. Alright, let's go ahead and look at our opposite one. So remember, so we can have gases, liquids, and solids. And now we can go the opposite direction. So remember that gas to liquid is called condensation. And this one is going to be exothermic, right? So these are all, we're going to do the opposite three processes. Liquids to solids, that's freezing, which is also endothermic. And then the last one, the opposite of sublimation, is called deposition. And that would be how you would turn carbon dioxide gas into dry ice. And so all of these would be exothermic processes. And in fact, this kind of cycle is exactly what's happening in your air conditioning and your refrigerator. Not a swamp cooler. Well, actually, kind of a swamp cooler. It deals with delta H, but typical, like a refrigerator AC or a car AC works in this way. So this is, again, just for your own kind of like interest. I'm not going to test you on this, so okay. Oh, forget it. I can't draw all these coils and stuff. Anyways, this is your refrigerator, or rather the like mechanism for cooling it. So what happens is you have a liquid in here that I'm going to draw in happy blue, although it is not a blue liquid usually, that tends to boil at a low temperature. So common ones that are used for this would be like pentane, which boils at like 35 degrees Celsius or so, pretty low. And so what happens is, as so part of this is connected to the refrigerator, like inside, and part of this is connected outside. So it turns out the heat from your food, or your inside of your car or whatever, goes into this liquid, which causes it to boil, and up it goes to the other side of your fridge. I don't know if you've ever felt this, but if you ever go towards the back of your fridge, you'll notice it's actually pretty warm back there. And the reason for this is once that liquid boils, it turns into a gas. It goes up these, coolant tubes and all that stuff. It goes to the radiator in the back of the fridge, where it lets off that heat. And so that heat that's given off ends up in the back of your fridge, like as in, behind it. So like not inside the fridge, but behind it. Or some fridges, they put it out on the bottom. So you're going to notice that part of your fridge, mechanism is going to be hot as a result. And that's going to be as this gas condenses. So remember that as the gas condenses, condensation is an exothermic process. It's going to give away that heat. And so behind your fridge, it's going to heat up the air back there in exchange. So you're going to be taking the inside of your fridge, the part that you want to be cold, the heat from that is going to boil up a liquid. That liquid turns into a gas, travels behind your fridge, and condenses, which gives off heat. So you have a compressor in the back that's going to help kind of force it to condense, and that's where the heat is going to be spit out, basically. So all we're doing is transferring heat through this mechanism. So that's just how it works, basically. So again, that's just food for thought. There's not really, I'm not going to ask you any questions or something like that on this. So cool. That's how this all works. So, fun fact, this fact you will need to know, is that during state changes, temperature does not change. So that means when your water is boiling on the stove, once it has started boiling, it's going to be the same temperature no matter what until all the water is gone. And we all know that takes a long time, right? So if you set a pot to boil on the stove, maybe it takes 10 minutes to get to boil. If you stick a thermometer in there, you're going to see it's roughly about 100 degrees Celsius. We're a little bit higher in elevation here, so it might be a little bit less than that, but that's okay. Come back 2 hours later, your water's still boiling. Stick your thermometer in, it's still going to be 100 degrees, or whatever temperature that you happen to read before. So during a phase change, there is no temperature change that's happening. So in the same with ice water will always be 0 degrees Celsius. So as long as you're stirring it or something. So as long as there's two phases going on at once, ice and water, or water and water vapor, water and steam, your temperature doesn't change as you put in more energy. So we're going to see that we have a different... have we calculated stuff? Yeah, we did like to freeze the water bottle, right? Let's just remind ourselves about that. How about, I have to look up a constant for you guys. Let's see. How about we do, heat of vaporization. There we go. Okay. So let's say that we have some ammonia. And let's say we have 125 grams of it. And it turns out that this ammonia, at its particular boiling point, has a delta H vaporization equal to 1,371 joules per gram, or 23,350 joules per mole. They're the same thing. Let's see what is the heat required to boil / evaporate this ammonia. Okay, y'all work on that for a second. I'm going to see if I can't get this silly webcam to work. Because now it's just bugging me, Okay, so you work on this. I pretend that I know what I'm doing with this webcam. Where are you hiding? Ah! Hooray! Giant version of me taking over the screen. Let's make me a little bigger. Yeah, there we go. That makes me happy. Okay, things are back to normal. That's good. Except it's kind of on the side. Let's fix that. Okay. Has anybody got a calculated answer yet? Okay. Sherry, that might be a little high. You might have to do one more step related to that. But let's go ahead and look at it. Yep. So remember, the kilojoules is going to be, we're going to need 10 to the third joules, 1 kilojoule. So just, yeah, exactly. One more little step we have to do. And I'm going to trust you on the math. What are we going to do about sig figs? How many sig figs do you think we're going to need for this one? You should have 4 of them, right? We have 4 given in our delta H. We have 4 given in our mass. Oh, Sherry, we have to send you back to sig fig learning camp. You have 4 sig figs here, 4 sig figs here. So yeah, get out of here. Okay, so that's going to be our answer here. Let's just double check. So this is boiling and evaporating. We have a positive number here. Do we need to change the sign on that? Let's just say we've forgotten. Let's go ahead and find boiling up here, or evaporation. It looks like that should be a positive number according to this happy little chart here. So we're okay, we don't need to change the sign. Okay, so we're good. So I'll just write that kind of as a note. The heat required to condense of this would be the same thing, but negative. Okay, so just remember that. I'll put this in giant parentheses. So remember, just the opposite transition would be just the negative amount of that. So if we were to condense, condensation is exothermic, so we would have a negative heat change. Alrighty, any questions on that one? Alrighty. Oops. Let's look at now instead. So this was talking about phase changes, so going from solid to liquid or liquid to get whatever. Now let's talk about how does heat relate to temperature in single phase systems. So single phase means it's all solid or liquid or gas. We do not have multiple phases at once. And so for this, we are actually going to have a new term, which is C, which is known as specific heat capacity. And C is given in the units of joules per gram degrees Celsius. Or you could have it in joules per mole degrees Celsius, either way. We're going to see these are kind of our more common units. So looking at them, we see we have a heat component. We have a temperature component. And we have a quantity component. So whether that's moles or grams, just use whatever you're given. So if we look at that, we can maybe kind of come up with a little formula here. If we know that this specific heat capacity thing has these units, that tells us that the units are can give us a formula. So you're going to hate this, but the letter we use for heat in this case is going to be Q, which sucks, but it's the way it is. So this is going to be our heat. And then let's use dark blue. We're going to see that this is going to be our quantity, which is either mass or moles. And that is the temperature change. And so we're seeing that delta thing again, the triangle. Remember that delta is always going to be your final state minus your initial state. So that's going to be your final temperature minus your initial temperature. I'm going to tell you one more thing. You can use either Kelvin or degrees Celsius for this. You're going to get the same answer. Believe me. Trust me. I know you don't trust me. Let's go. I'll show you. Okay. And then we're going to come back to this. Actually, let's come back to this first, and then we'll talk about the temperature some more. So if we see that by putting in our units, we saw that Q is going to be our heat, which is going to be in joules. We're going to have a quantity component, which is mass or moles. And again, I'm just kind of copying from the units here. The units are going to give us our formula. And then, of course, we have the temperature change. So we know where we're putting in heat to this. We're expecting the temperature to change. So if we rearrange this, if we move this stuff over to the other side, we get a lovely equation. I often refer to this as MCAT because it kind of looks like that. So if any of you are going into medicine or whatever, that's the test you'll have to take, right? So that's how I remember this one. So remember again, this is your quantity. That's your specific heat capacity. Oops. That's not the right one. And again, that's going to be change in temp. These formulas are the same. I've just moved m and delta t to the other side of the equation. Poor Oz. He's just choking and dying. Poor little thing. Okay. So, how much heat is required to heat, let's say again that 125 grams of water from 0 degrees to 37 degrees. And let's say we have our, what is K? Kelvin? That is one of our potential temperature units. So you can use either one. You can use either Kelvin or Celsius here. These in fact will be the same number. They would be the same. Okay. You do not ever need to memorize these numbers, but if you take 111, you're going to deal with waters very often. So, anyways, let's go ahead and heat up our water. So, from this little sentence here, we should be able to pull out all the numbers that we're going to need for this calculation. All right, we have here's a number, another number, and a fourth one. Which number is which? What is that 125 grams going to be? $125 grams is Q. What's the what does grams represent as a unit? Does grams represent heat? So remember, we have heat, we have amount, and we have change in temp. Yeah, so I like Sherry's answer. Yeah, it's the quantity, it's the amount, right? Which unfortunately is not Q. Go figure. But that's the way it is. So we're actually looking for the heat, right? So we're going to leave Q alone. We have 125 grams. No, don't be sorry. We're learning. This is a normal part of learning. Okay. What else do we have here? Which one is going to be our C? Hopefully should be obvious because I wrote it exactly like that. I'll just copy it because obviously the C is written as C over there, so we're okay. Last thing we need is this delta T idea. And so remember that delta T was temperature final minus temperature initial. Which one of these is going to be our final temperature? Yeah. And so therefore our initial temperature would be 0, right? So just to note that this was our final and this is our initial. Did I spell that right? Yeah, it looks like it. Okay. So doing all this fun math, let's do it real quick. 4.184 times 37. Okay. So doing that, I get 1,900, or this number. I don't know how to read numbers, but that's what we get when we calculate this. Let's have a look at what our unit is. We're going to fix the sig figs, don't worry. So if we look at this, it looks like grams cancels out. We see that this thing put together is just 37 degrees Celsius. All right, subtracting 0, we don't need to worry about that. So that means degrees Celsius will cancel. So we're left with this unit here. So that means our unit that we're ending up with is joules, and that should be what we're looking for, right? We're solving for heat. So okay, I did not ask for a unit, so yeah, we'll leave it in joules. That's okay. Let's look at the sig figs. From all this stuff, it looks like we're gonna have 4 sig figs. So we're gonna need to round it accordingly. And that would be our answer. So it would take that many joules to heat up that water. Alrighty. Just so we know, I'm going to show this to you in Kelvin, because this apparently is an area of confusion. So, even in 111, still sometimes people will make this mistake. Do we remember that Kelvin is degrees Celsius plus 270 or 273.15? So if we do that for our two numbers, and then if we do it for 0, we can convert them to Kelvin. So if you really wanted to, you could plug these numbers instead. I'll just do it down here. Lo and behold, magically, it's just 37 still. So it does not matter if you want to use Kelvin, you can go right ahead. It really does not matter. A change in Kelvin is the same thing as a change in Celsius. So you may see specific heat capacities given to you as like joules per gram Kelvin. Doesn't matter. You can just you can replace it with degrees Celsius for this particular sort of thing. So anytime you have a change in temperature that's Kelvin, it's the same thing as the change in temperature of Celsius. We're going to see next chapter, we're not going to be working with temperature changes anymore. We're going to be just looking at single temperatures. In that case, it's not going to work. But since these are change in temperatures, they're the same. So doing all that stuff, if we wanted to use Kelvin instead, we would still get the same answer because it's still 37 is going to be your change in temperature. Okay, so that was just a blurb to remind you that, or let you know rather, that you do not need to use Kelvin if you don't want to here. If you see specific heat capacity for water, again, this was 4.184 joules per gram degree Celsius, is exactly the same as gram Kelvin. Okay, so don't worry, don't be afraid. You're good. Okay. Did we have any questions on that problem we did, or this idea of the change in temperature units? I'm going to just scroll up for a minute. Let's just go back to the problem here. Did anybody have any questions on this part? Plugging in the numbers. Okay, I'm not seeing any. So, if something does come up, of course, always, yeah, that's okay. But yeah, if any come up later, just go ahead, write them out. We'll see. Okay, then in that case, I want you to know one more thing. Oops. It turns out we have another unit for heat that we use. This one we actually use in our daily lives quite a bit more. It turns out that 4.184 joules, notice the specific heat capacity of water, is equal to 1 calorie. So a calorie is also a unit of heat, a unit of energy, that happens to be equal to that number of joules. So the C for water is just 1 calorie per gram degree Celsius, but you don't need to memorize that, but that's why calorie is... Okay, that's why calorie is... that's how it's defined. One more thing to note... Oops. Unfortunately, we have this other unit, which is calorie with a capital C, which actually is a kilocalorie. So this is the calorie we see on our foods. So if you're looking at your bag of M&Ms or whatever, you'll see this calorie, the calorie with a capital C. I'm not quite sure where this calorie came from, but it's annoying, but you'll only ever see this one on nutrition labels. So we're not going to see it in chemistry, but I thought I would help you to understand real life. So you've heard of calories before, right? But actually the calories that you're thinking of is capital C calories. Interestingly, if you go to Europe, you will see... instead of like the calories that we see, they will either write kilojoules. You'll see either really anywhere besides America, you'll see other units for on their nutrition labels. So of course we must always be different. So if anyone's been to another country, you'll be more familiar with seeing nutrition facts as kilojoules or kilocalories. Okay, so again, that's just a unit thing. So you may see calories in your everyday life, but no, that's a special case. Okay? Coolio. Speaking of which, then, here's another problem for you. So I don't want to go to the gym anymore. But also, I mean, I wouldn't because of COVID, but pretend this is not COVID, and I could have gone if I wanted to. And let's say that I would have burned 300 kilocalories. That's the same thing as 300 calories. That's what, like a donut? One donut or something, right? So if I work hard, that's probably about half an hour on one of the cardio machines for me. Let's just think. How much ice water (0°C) would he need to burn those calories? Just so you know, temperature final for a human body is 37 degrees, right? That's something you'll be familiar with since most of you are going to healthcare. In Fahrenheit, that's 98.6-ish. For Celsius, it's about 37. So that's why I used that number earlier, I guess. But let's look at this problem now. So I want to skip going to the gym because no one wants to do that. But the gym would have helped me burn 300 calories. Or in chemistry terms, kilocalories. So if I could do this by drinking ice water instead of actually doing any exercise. So let's go ahead and see how this is going to work. So what numbers do we have from this paragraph? We've got our formula. What's the 300 kcals? Oh, I guess I should put specific heat for you guys. What's the 300 kcals? What letter does that represent in our formula here? Brittany, no! Kilocalories. So kilocalories is a unit of, let's see. So if calories and joules represent the same thing, they're both units for the same thing. If we saw last time that Q was in joules, right? This time we have calories. It's heat. So calories are a unit of heat or energy. So this time it's Q. I feel so bad for you, Brittany. I feel like I've let you down here. So, what color am I using? Light blue, why not? Yeah, we will get this. Was it 300? Yeah. 300 kilocalories. Alrighty. What other numbers do we have here? I see a 0. What does that 0 represent? I'm gonna put the C in just because. Yeah, it's one of the temperatures, right? And in fact, that's gonna be our initial temperature, right? The ice water is at 0 degrees Celsius. I'm gonna drink it, and then it's gonna become 37. Yeah, exactly. Perfect, perfect. So in this case, we are missing M, right? And we can tell because we're asking how much ice. That's what the question is asking. So we're looking for the quantity of ice water, or not ice water. Um, and exact. That's our what we're looking for in this case. One thing that we need to look at, we see that we have. Let's use green actually. Well, maybe I should use black. We have calories here and kilocalories here. So we should probably adjust those. We could adjust either one. But I'm going to just go ahead and adjust the one on the left. Kcal. Just going again, we're using this kilo thing. I'm just putting in scientific notation for sig fig purposes, but trust me on the math here. Okay. So we just have to make sure our units are going to be the same, so we can cancel them out happily. So if we read-write this, and I'm already going to subtract 0 because who cares about 0? Let's go ahead and look at our units now. So we have calories and calories. Those cancel. Degrees Celsius cancels. So if we go ahead and solve this equation, we're going to end up with grams, right? So let's do this. I guess technically divided by one, but who cares about one? Let's see. Let's do the math. 3 times 10 to the 5th divided by 37. We do the math, we get 8,108.1 grams. Yikes, that's quite a lot. Sig figs, how many we need? Looks like we're going to need about 3. Just so we know, this is about 2 gallons of ice water. So, probably not the best way for me to be burning my calories. There is pretty much no way I would be able to drink that without like dying. So, unfortunately, I guess I'm gonna have to go to the gym. So, that's very sad times for me. Alas. Cool. So, let's kind of step back and look at that one more time. So we were able to pick out the numbers from the problem. We have a unit of heat that's given. So I normally would have burned 300 calories at the gym, apparently, and so I'm going to drink ice water instead. which starts at 0 degrees and will end up at body temperature, which is 37 degrees. And we were given a specific heat capacity. So we also saw that we're looking for a quantity of ice water. That's what the problem was asking for us. So we were looking for M. We're able to plug in all the other numbers. Yes. Well, so coffee is a water-based solution, right? So it would really be pretty much the same. I guess. Okay, fine. Let's do it. Let's do it. Okay. And yeah, and so from that we just had to make sure our units were the same, and then we got our answer. And so we then found out that it would probably not be realistic for me to skip the gym if I really wanted to burn those calories actively. So let's say that I drink my coffee at 95 degrees Celsius, which is probably absurd. I usually don't drink it that hot at all, but we'll pretend. And let's say that I have, just trying to give this to you in like good numbers. So if I'm drinking 10 ounces, that is about 1 point, no, 0.2, okay, we'll say I'm drinking 275 grams of coffee at 95 degrees Celsius. We're going to be using this 37 everywhere here, but that's okay. Oops. Okay. So I'm now going to be drinking my coffee. And we're going to say approximately, because coffee is mostly water, we're going to say again it's going to be about that 1 gram or 1 calorie per gram degrees Celsius. Okay. Time to pick apart the question. What does 275 represent? This one's for Brittany. Alright, you've got this. You can do it, yes, don't worry. Just look at the unit. Is that a unit of heat, of quantity? Is it a specific heat capacity, or is it a temperature? Yes! So that's our mass. What does 95 mean? Brittany. Not quite. So here, this is, let me, okay, we're gonna just make this super good for us. So, here are the units of these quantities. Yeah, it's the initial temperature. Yeah, you're absolutely right. So here are the units that we're going to be associating with these quantities. So Q, which is heat, is either in joules or calories, or kilojoules, kilocalories, whatever. This refers to a quantity, which is going to be how much of something we have, either mass or moles. Specific heat capacity, it's a constant. And then this, of course, is the temperature. I guess I can write specific heat capacity. Okay. Great job. T initial. Alrighty then. So next number I see is 37. No, I totally get this. Yeah, it can be confusing. So what does 37 represent? Yes. So that is our final temperature. And then, of course, C is given to us. So let's just go ahead and look at the question. The question is how many calories? So that's telling us that we are solving for Q. Since Q can be in calories, that is going to be the question that we're asking. Okay, so let's scroll down a bit here. All right, so we're looking for Q, so let's go ahead and plug in our numbers. So it looks like our mass was 275 grams. We are our specific heat capacity. And then our temperature change. So remember, it's always T final minus T initial. Yeah, exactly, we're solving for Q. So the T final remember, it's always final minus initial. Alrighty, if we do that, I'm just gonna do this part first because we must do this parentheses stuff first. So 37 minus 95 is going to be negative 58 degrees Celsius. Yeah, of course you got it right. Okay, let's go ahead and look at our units. Grams cancel, degrees Celsius cancel. We're going to be left with calories. So let's go ahead and do the math. 275 times negative 58. Oopsies. Oops, I don't need red for this. Equals negative 15,950. Sorry, let me just go ahead and erase that. And that's calories. And looking at that, we're going to need 3 sig figs. So let me actually go ahead and fix that. Oh no, we're going to need scientific notation. 1.6 times 10 to the 4th calories. You'll note this is negative because this time we cooled down our coffee. And so it had actually given me energy, and so that's why it's negative. It's the opposite. So when I burned energy, that was positive, and now that I'm getting energy, it is going to be negative. Okay, but just so we know, because the temperature had decreased, that's why it's negative. Okay, so drinking my coffee, they always say coffee is 5 calories, right, or whatever, black coffee that is. And then, so apparently drinking it while it's hot, I will get more calories out of that, which is awful. So, lesson here is always drink your coffee at room temperature. Yuck. But however, that's all I have left at the end of class anyway, so it's gone down to room temperature. So, cool. We have done some fun calculations today. And so we have succeeded in our math. Tomorrow we are going to just finish up this chapter, talking about solids more, and just different types of solids, and then we're going to start our next chapter, which is on gases. So I'll try and put up homework for you guys so you can have fun working through these. Okay. With that, I'll see you all tomorrow. So have a great day. It's Monday, the worst day of the week, but we'll get through it together. Alrighty, see you tomorrow.